Okay, this is going to be the lecture for lab number 2, which is going to be dealing with intermolecular forces. We're going to deal with intermolecular forces quite a bit. What are intermolecular forces? Well, interatomic forces would be bonds, right? We can have ionic bonds or we can have molecular bonds. Intermolecular forces are those forces, attractive forces usually, between different molecules. All right, and there's really several different kinds of intermolecular forces, and they have different strengths. Dipole-dipole interactions exist. That's more or less dispersion forces. Dispersion forces happen usually between what we would call organic compounds, oils. Oils are held together by dispersive forces. That is, there's not a strong difference in electronegativity. There's not a strong difference in the charges on those items because they're carbon and hydrogen, which has very similar electronegativities. But there is still an attractive force because there can be momentarily and sudden ions that form due to the electron swarm around the molecules that have them come together and have some cohesive force, but usually it's very, very weak. There's also dipole-dipole attractions, and those are from actual dipoles. When you have a molecule that actually has a polarity to it, the positive side is attracted to the negative side of another molecule, the negative side attracted to the positive side. And there's one special case of that, and that's called hydrogen bonding. And that happens anytime you have a hydrogen bound to an oxygen, a nitrogen, or a fluorine. Although the typical ones are nitrogen and oxygen. They're the most common ones. You can have it with fluorine as well. And then the final one is ion-dipole interactions. And this is going sort of in strength, going down them in order of strength. And ion dipoles are very, very strong because there's an ion involved with it. So, typically this would be ions that are molecules that are ions like ammonium and things of that nature, as opposed to really ionic bonds that are between the atoms usually, or sometimes they're between atoms and molecules. But ionic dipole, the dipole from one thing and an ion for another, that's a very, very strong bond. So you need to sort of understand those, then hopefully you've covered that stuff in the lecture, because I don't have a lot of time to go through all that, because I don't want this lecture to end up in the lab being too long for it. But we need to go through some things that you will need to be able to do this lab. So let's get started on covering those sorts of concepts and ideas. The first one is they're going to want you to draw some Lewis dot structures. And you covered Lewis dot structures in General Chemistry 1. Everybody covered Lewis dot structures in General Chemistry 1, and then you've forgotten most of that is for that. So my handout that you should have in front of you to follow along with this lecture, my handout covers how to do Lewis dot structures to refresh your memory. Basically, you draw the skeleton of a structure. That is, you put usually the atoms with the highest valence. And what's valence? Valence is the number of electrons on the outer shell. Sometimes you can think of it as the number of electrons missing on the outer shell compared to the octet rule, because that is areas where bonds can form from other electrons. Or the largest atom goes in the center, and if it comes down to where the size are about the same, you put the least electronegative atom in the center. And then what you do is you count the total number of valence electrons that you have available, and that including charges. Remember, if it has a negative charge, it's going to have an extra electron. If it has a positive charge, it's missing an electron. So you figure up that number. You put the smaller atoms around the central atom, and then you connect everything with a double bond. That means it takes two electrons. Single bond, I'm sorry, not a double bond. A double electron bond, which would be a single bond. You connect everything with a single bond. That uses up two of your valence electrons. So you take your electrons that you have remaining after everything is done with a double bond, and that's where you have to make some decisions. One of the things is that you really want to satisfy the octet rule for both the surrounding atoms and the central atom. But remember, the octet rule is really just 2 electrons for hydrogen. And hydrogen shows up a lot in these sort of structures. So you don't put 8 electrons on hydrogen. Hydrogen is just a proton and an electron. So that for the bond for it, it only needs 2 to satisfy its shell, because it only has what you could consider to be an S shell, and that just takes 2 electrons. So once we satisfied that, if we have any electrons left over, we would tend to put those on the central atom. That is, if it should satisfy the octet rule, 8 electrons total. unless it's from the third period and below, and then you can kind of shove extra electrons on there. If you satisfy the octet and you still have electrons left over, and it's only in the second period, right? The second period, that's like the carbon, the carbon and nitrogen and fluorine where they all are. Then you would try to look to make double bonds to use up the electrons in some special way of forming them around to be able to satisfy the octet rule and use up all the electrons around it. If it's third period or below, you can just kind of dump the extra electrons in pairs on the central atom. That would be where you'd put those. Hopefully, I'm going through it very loosey-goosey. I'm not really explaining these things stuff. We'll do a couple of examples quickly on how to do it, but again, this is all review, so I don't want to spend too much time on this. I want to be able to spend the time on the actual lab. But since we're going to go ahead and do something with the paper, let me switch it over. This is not as easy to do with my with this compared to what. All right. So let's do an example. Let's do an example of something very simple, 2 chlorines. So we know what chlorine is, right? Chlorine is Cl, and we have 2 chlorines. Chlorines are group, 7? So each one has 7 electrons around it. Since we have 2 chlorines, we have 2 Cls, which is equal to 2 times 7 electrons. We have a total of 14. Since there's no decision as to which one's the central because we only have 2, we'll connect them with a single bond like that, and we have now remaining 12 electrons. Where do we put them? Well, there's no central atom or outside. They're all the same, so we put them in pairs. Remember, they always go in electron pairs. That's a pair, and we put a pair here, and we put a pair here, we put a pair here, we put a pair here, put a pair here, put a pair here. You write them like that, and they go to the 4 locations around the atoms, and that would be 2, 4, 6, 8, 10, 12, 14. We've used them all up. I know sometimes you'll see that they write these pairs by doing them like this. Yeah, don't do that. Just put a single line in there for the bond. It just makes it cleaner, and it's much easier to recognize as to what's going on. So that was a very, very simple one, an easy one to do. Let's do a couple more, make sure that we understand what we're doing here. So let's draw the methane, right? Methane. So methane is what? Methane is CH4. So that's CH4. That means we're going to have how many valence shell electrons? Carbon has 4, hydrogen, each one has 1. So we have 4 plus 4 times 1, and that's going to be 8 electrons total. That's how many electrons we had to deal with. Carbon, much, much bigger than hydrogen. And hydrogen and or the group 7 atoms like chlorine and fluorine and bromine, those almost always are exterior ones because they only have a single electron that they can share. So in this case, of course, carbon's going to be the center. We would place the 4 others around it at the 4 locations, the 4 sort of compass points that we have for it. We'd attach each one with a single bond. We've used up 2, 4, 6, 8 electrons. Let me move this up so you can see. We've used up 2, 4, 6, 8 electrons. That's what we had. And we've satisfied the octet rule for carbon. I forgot to check that octet rule with all chlorines, but we did 2, 4, 6, 8, 2, 4, 6, 8. Octet rule satisfied, octet rule satisfied. 2 for each of the hydrogens. We're done. That would be the Lewis dot structure for that. All right, let's try do one more. I just want to cover this stuff, make sure you understand. Let's do ammonia. Ammonia, what's ammonia? Ammonia, remember, is NH3. Okay, so again, we have hydrogens. We know hydrogen has a valence of 1, therefore hydrogen is going to be the outer. Let's put the larger atom in the center, that's the nitrogen, and then we'll put the hydrogens around it. And we only have 3 hydrogens, so we can only put the hydrogens in 3 places, and we'll connect them with a single bond. How many electrons do we have? Well, nitrogen is a group 5, therefore it has 5 electrons, plus hydrogen, each one has 1, 3 times 1. So we'll have a total of 8 electrons again, just like we had before. We've got 8 electrons possible. We've used 2, 4, 6 electrons. So we've used 6 electrons. We have 2 electrons left over. Where do they go? They go in the central atom. Put the 2 electrons there. And you can see that that's necessary to satisfy the octet rule. 2, 4, 6, 8. We've satisfied it for nitrogen. Therefore, this must be the correct structure for it. You could write this with the electrons on the bottom and a hydrogen on top, or the electrons on the side and the hydrogens in these 3 positions. I just always do it with the electrons on top because it will make it a little bit easier when we get into something else that we're going to have to get to. Again, I know I'm rushing through this, I'm sorry, but kind of got to do it because this is all a review for stuff you should know, and we've got to get through some other stuff that is a little bit more complex, and I want to cover everything, but I can't cover it as in-depth as they would in a lecture necessarily. If you have problems, email me. We can set up a Zoom. Meeting with several students or just one student, and we can go through and cover some of this stuff. Let's try one that's a little bit different. It's a polyatomic anion, and that's ammonium. Ammonium ion. So ammonium ion is what? It is NH4 plus. Now, the plus tells us what? The plus tells us that there's one less electron than we would normally have. So we know nitrogen has 5. Each hydrogen has 1, so 4 times 1. But there's going to be minus 1 in this case because that's where we get the positive charge, is we're minus 1 negative charge. So 5 times 4, 5 plus 4 times 1 is what? 9 minus 1, we have, again, 8 electrons just like we had before. We're going to draw it the same way. We're going to write the nitrogen in the center. We're going to put the hydrogens at the 4 corners, the 4 compass points, sort of. We're going to connect each one with a single bond. That's going to use up 2, 4, 6, 8 electrons. And we say, oh, okay, well, there's none to put on the central atom, but we know that this has a positive charge overall. That's why we took off the 1 electron. If it has a negative charge, if it's an anion with a negative charge, you add an extra electron in. Now, how we put that positive charge and where it's associated, that all comes down to formal charges. And formal charges, whereas you should know, you should have learned all that stuff. I don't want to get into that because that is just a little bit more complicated than we really need to be able to do for what we're doing on there. So those are some Lewis dot structures that are pretty easy. Let's do 1 or 2 more, just so you can't say I didn't cover everything. Let's do some simple ones. How about carbon dioxide? Carbon dioxide, you know, CO2. Well, we're going to try to decide, do we put the carbon or the oxygen in the center? Well, they say use the larger of the two, but the larger of the two, notice that's the second step you go to. The first one is highest valence. Which one has the higher valence? Carbon, because carbon has 4 lone electrons around it, right? And oxygen oxygen is group 6, so it has 6 electrons. This has 4 electrons. That means it has 4 places to get to the octet. Oxygen has 2 places to get to the octet. So we're going to put the carbon in the center with the 2 oxygens around it. And we have how many electrons? Carbon has 4 plus 2 times each oxygen has 6. That's going to be 12. So we have 12 plus our 4, and that's how many? That's 16 electrons. We've used 2 4 electrons, therefore there are still 12 electrons left. I could put them as 2, 4, 6, 8, 10, 12. There we go. So I've used all the electrons now, and I've got my structure. Now I have to check it. Octet rule satisfied? 2, 4, 6, 8. Yep. 2, 4, 6, 8. Yep. No, not for carbon. Carbon does not have 8 electrons around it. It only has 2, 4 electrons, not 8. It does not satisfy the octet rule. Carbon is not a group 3 or below, therefore we will satisfy the octet rule. So to satisfy the octet rule, what do we have to do? Well, I can pull a lone pair off of here and create a double bond. That means that this pair of electrons is shared between both of those. So there's 2, 4, 6, 8 here. That works. 2, 4, 6 here. That doesn't work, but I can pull another pair off of here, add a double bond in there. Now I have 2, 4, 6, 8 around the carbon. I have 2, 4, 6, 8 around the oxygen. 2, 4, 6, 8 around the oxygen. Octet rule is satisfied. Therefore, I've drawn the correct structure for carbon dioxide. Okay, how about one a little bit different? How about sulfur dioxide? Sulfur dioxide is SO2. Since sulfur is a group 6, we have 6 electrons that are there, plus we have, what, for our 6 times, 2 times the 6 electrons for each of the oxygens. I have 12, I got 18 electrons total. 18 electrons total. What am I going to do? I'm going to draw, it says the more electronegative one in the center. Well, it says the one with the greater valence, but these are both the same because they're both group 6. So I would draw the larger in the center, that's the sulfur, and put the oxygens around it, connect them both with a single bond. That's going to use up 2 4 electrons. Minus 4 gives me 14 electrons remaining. I'm going to put them on the outer atoms. 2, 4, 6, 8, 10, 12. Well, I got 2 electrons left over. Well, where do I go? I put them on the center atom. Okay? Now I check for the octet rule. 2, 4, 6, 8. Yep. 2, 4, 6, 8. Yep. 2, 4, 6. No. Not satisfied. So I'm going to have to do something to satisfy the octet rule. What will I have to do? Well, I can do the same thing I did before, but I don't need both of them. I just need one. So I can do that now. I have 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. It's all satisfied. I could write this either way. I could also write it as, yeah, well, if you're going to write it different, then write it different. That would also satisfy the octet rule for everything, and it would satisfy the structure. So either one of those could be done. All right, so let's draw, let's do one more, just a little bit strange one. Let's do one for CH4O. Wow, CH4O. What will we do? Well, highest valence, that's going to be carbon, because carbon is 4, and that means it can take 4 electrons. So when they say highest valence, they mean highest number of possible bonds that could be formed to it. Carbon has more possible bonds formed to it. So let's put it in the center. I've got 4 hydrogens, so I could put, whoops, I'm not put a bond in there yet. I could put the 4 hydrogens at the 4 corners, but if I put the 4 hydrogens at the 4 corners, then where do I put the oxygen? I can't have a bond coming off of a hydrogen to an oxygen like that, because I'm already going to attach these with bonds to the central carbon, right? So if I have a bond going to hydrogen there, I can't put another bond to it to oxygen. That isn't going to work. So the only thing that would make sense would be if I put an oxygen there and then put another hydrogen, because that would work. I can have 2 bonds to the oxygen, but I can't have 2 bonds to the hydrogens. So if I do that, how many electrons do I have? Well, carbon's got 4, plus 4 times the 1 for each hydrogen, plus 6 for the oxygen. So I've got 4, 8, and 6 is how many? Well, 4, 8, and 6. That's going to be what, 14 total, right? I mean, we're going to have 10 and 14 is the way you want to look at it. I've used up 2, 4, 6, 8, 10. Remember, I have 2 in each one of these bonds, so 2, 4, 6, 8, 10. So I've used up 10. I have 4 electrons remaining. So where would I put it? Well, octet rule for the carbon, 1, 2, 3, 4. Yep, 2, 4, 6, 8, it's satisfied. Octet rule for the hydrogens, which is just a 2, that's satisfied. Octet rule for the oxygen, no. I've got 4 electrons, let's put them on the oxygen. Now the octet rule is satisfied for the oxygen, for the carbon, and for the hydrogens. This is a hydroxyl moiety, is what you would call it in organic chemistry. This indicates that this is an alcohol. Anything that has this OH group on it like this is considered to be an alcohol, okay? Including the, as Homer Simpson said, the source of and solution to of all life's problems, which would be ethanol. This is not ethanol. This would be methanol, but still, this would be an alcohol. Anything that has that as an alcohol. Notice, oxygen bound to hydrogen. What kind of bonds could it form? Yes, it can form those hydrogen bonds that we were talking about before. So these are things you need to know. One other thing that the lab is going to want you to be able to do, and I know this is a ton of stuff, and I know I'm running through it fast. This is a video you can watch multiple times, so I'm going to be going fast because I've got to, just because of the time constraints. Sorry, we've got to adjust for this weird situations that we're in. One of the things else you're going to do is determine the polarity of these molecules that you're drawing. To determine the polarity, you must use the Vesper theory. That's VSEPR. That stands for valence shell electron pair repulsion theory. Hopefully you remember this. In Vespa, you can have simple molecules with no non-bonding electrons. There's basically 5 shapes. It can be linear. And linear would be something like boron difluoride. We do something like that, and then of course you would have electrons out here for the fluorines. And what that says is these two bonding electrons, because this is valence shell electron pair repulsion theory, because there's a pair of electrons in these bonds, they want to be as far from each other as possible. So to do that, they spread out and form a linear shape. That puts them as far away from each other as they can be, because linear is going to be the farthest they can be on that atom that goes around it. And that's called linear. There's also a trigonal planar. Planar shape, and that's if we have 3 atoms around a central atom. So if I had the boron and I had 3 fluorines on it, like this, and of course all the fluorines would have electrons on them. But notice that this is spread out. These pairs are spread out in a way that gets them as far away from each other as possible, and that is trigonal planar. They're all in the same plane. There's 3 of them, so they're trigonal planar. The final one, the other one that we're going to go through, because it's the only other one you really need, is what would be the shape around these molecules for the 4. There's 4 things around them, right? Pairs. Remember, we're dealing with pairs. 1, 2, 3, 4 pairs around them. It's the same as the 4 pairs for our CH4 that we had, and that's going to be done in a trigonal shape. Okay, so the way we draw that is trying to do a 3-dimensional structure here. We do it like this, and that is, this one goes back into the paper, this one comes out of the paper, and these are both in plane with the paper. And this forms what's known, so you have this repulsion between here, repulsion between here, repulsion between here, repulsion between there, and this forms a tetrahedral shape. Tetrahedral, tetra, 4 things, tetrahedral shape on there. Okay, and that's very similar, to a lot of things. That's what these would. These would all be tetrahedral, but in this case, it would be the fluorine would be here, and then there'd be a lone pair of electrons up here. There'd be a lone pair of electrons out here. There'd be a lone pair of electrons over here, and there'd be a lone pair of electrons one of these would be a bond. Sorry, one of these would be a bond. The other one would all be lone pairs, right? Because there's 3 lone pairs plus the bonding pair. Remember, valence shell electron pair repulsion theory always deals with electron pairs. Okay, so those are the 5, well, it's only 4 of the 5 basic shapes. I'm not going to get into all of them. And then when you look at them, there's some other shapes that happen. Like I said, this one, there's only 1 real bonded to an atom. There's 3 others that just have electrons on it. So if you looked at the overall structure of that, it would appear to be linear, but I don't think that's going to be as important for what we need to do. You need to be able to do these only because you need to be able to get the shape of something to decide whether it's polar or not. For instance, water molecule. We know what a water molecule is, right? It's H2O. So if we draw that oxygen in the center, we put the 2 hydrogens out like this. We have how many? 6, 7, 8 electrons total. That's going to use 4. And that's going to give us 4 electrons left over. Where do they go? You put them on the oxygen. But these want to repulse as far away as possible. So you say, well, that looks as far away as possible. Okay, it is, but there is more electron density in a pair that's non-bonded than there is in a pair of bonding electrons. And because of that, this kind of pushes these things over, and what you really end up with is you end up with a structure like this, where everything is separated as far as possible. And if you look at the overall shape of that, and you think, whoop, you can't see what I'm doing, so let me pull it up to where you can. You end up with that bent shape. Remember, you can't see electron pairs That's the way to think of it. You can't see electron pairs, but you can see atoms. Because we know we can see atoms. You can look at your hand. That's atoms. So we can see this. This is going to have a bent shape to it. Well, we know, hydrogen bonding or whatever, we know that the electron density here is slightly greater than the electron density down here. So this develops a slight negative charge on this side, a slight positive charge on that side, and therefore a water molecule is polar. Okay? So we have to be able to draw these Vesper structures to be able to decide the polarity of something. Something's only going to be polar if it has that sort of dispersion. It's not going to be symmetrical. I'll show you an example of that in just a second. So the other one we drew is ammonia. Remember we drew ammonia. We had N with this, and we had this, and this, and this. That's the ammonia molecule. But remember, this is going to be a tetrahedral structure, right? Tetrahedral because there's 1, 2, 3, 4 pairs around it, just like water was tetrahedral as well. When we looked at the water molecule, when we finally drew it correctly, we could draw it like this. It's tetrahedral because there's 4. 1, 2, 3, 4. We drew it like this initially, but there's 4 pairs around it. If it has 4 pairs around it, 4 in your mind tells you tetrahedral. Tetrahedral means it's drawn like that. Therefore, we have this negative side and we have this positive side. This is also tetrahedral. Therefore, I could draw it like this. And again, what are we going to see? Well, this lone pair is stronger than bonded pairs. So this pair of electrons has stronger repulsive forces than these other ones. So it kind of pushes them down and away, and that ends up creating a slightly larger angle between these. And so this would be a polar molecule because it would develop a slight negative charge on this end, a slight positive charge on that end. And guess what? Hydrogen bound to nitrogen bound to hydrogen can participate in hydrogen bonding as well. Okay? If something is completely symmetric around it, then it's not going to end up developing a charge. So that's one of the things to look at. You draw the structure, you do the Vesper structure of it. If it is completely like our carbon dioxide, what we have for carbon dioxide, we have, even though the electronegativity between the carbon and the oxygen, we know that the oxygen is much more electronegative than the carbon, and you would say, okay, well, this develop a slight negative charge here and a slight negative charge here with a slight positive charge in the middle. Because it's symmetric, it has no polarity. So it's considered to be a non-polar molecule. It has to have that division, it has to have that separation. It has to have positive charges in one area and negative charges in another area that's offset. They can't be perfectly linear or in a straight line, or there won't be any overall charge on it. Okay? So you have to be able to draw those things. You have to be able to draw those to be able to figure out what is the structure of them and whether or not they're polar. I think that covers everything. For structure, what was it? We drew this before when we had the boron trifluoride, right? And I said these have long pairs on them. And obviously the fluorine is much, much more electronegative than the boron. And therefore these would all have slightly negative charges to them. And this would have a slight positive charge to it. But because it's symmetrical, there's not one side that has a negative charge, one side that has a positive charge. The positive charge is in the center and it's surrounded by the negative charges. This is considered to not be a non-polar molecule. Why do you have to know whether they're non-polar or polar? Well, remember we discussed at the very beginning about the intermolecular forces, the attractive forces between these things is dependent upon what kind of bonds they can form, and that means you have to figure out what kind of bonds they have to be able to figure out what kind of bonds they can form to see how attractive they are to each other or or not. So that's something that you have to do. All right, so let's finally get into the lab we're going to do. Once you've figured out those things that you're trying to figure out and those bonds there, then we're going to get into performing the lab, and the lab is going to be dealing with those intermolecular forces. So we're going to look at the intermolecular forces between water. They have you try to do IPA, isopropyl alcohol. You're not going to find 91% isopropyl alcohol. I've got some stashed, but I'm pretty much a prepper, so I always have that kind of stuff. I've had it for a long time, just in case something like this coronavirus came along. But right now the stores are all sold out of 91% isopropyl alcohol. I doubt you'll even be able to find 70%. They say you can go get methanol. You can get that from buying some, what is it, windshield washer solution. So look at the windshield washer solution and make sure it's pretty good concentration of methanol in it. If it is, then buy that. If not, then buy a little bit of the 70%, if you can find it, 70% isopropyl alcohol to do this experiment. What we're going to look at is we're going to look at evaporative cooling. And evaporative cooling is going to be a measure of the intermolecular forces between molecules. What is evaporative cooling? Well, we know all about evaporative cooling in Florida. Evaporative cooling is when you sweat and the water gets on your skin and it then evaporates off your skin, and when it evaporates off your skin, it pulls with it a huge amount of energy, and that energy cools you down. Why doesn't it work in Florida? Because of humidity. Humidity is so great it just doesn't work, because you can't sweat. I mean, you can sweat like crazy, but you can't get evaporation of that sweat because the air is already saturated with water. We know ceiling fans, they're used a lot in Florida. Do ceiling fans cool the room? No, it actually heats the room because the running of that motor causes the room temperature to increase slightly. What the fan does was it blows air across your skin, which increases the evaporation of the sweat on your skin and cools you down, even as it's warming the room very, very slightly. Water, as I think we've hopefully touched on before, water is super special. Hydrogen bonding, super special. How is it so super special? Well, let's look at the amount of energy that is needed to be put into water to take it from 100 degrees Celsius liquid to 100 degrees Celsius gas. That is, no change in temperature, just a phase change. And also, well, first let's look at the amount of energy it takes to take, say, a gram of water and raise its temperature from 0 degrees, freezing, not frozen, this is both liquid 0 degree water, and heat it up to liquid 100 degree water. That's taking it from freezing to boiling, okay? Well, the enthalpy for water is 4.184 joules per degree Celsius. It's really Kelvin, and the reason everything is really done in Kelvin is not a scale. Kelvin is an actual measure of the energy of a system. So if I take something from 50 Kelvin to 100 Kelvin, I've doubled the energy of the system. If I take something from 50 degrees Celsius to 100 degrees Celsius, I have not doubled the energy. Okay, that's what Kelvin's for. Most people think, well, it's Kelvin because it goes to 0 and it can't go negative. Well, it can't go negative because you can't have negative energy. But really, the whole purpose of Kelvin is it's an actual measure of the energy of the system. Okay, so this is the enthalpy for the that's our enthalpy that we have for water. So if we're going to go from 0 degrees Celsius to 100 degrees Celsius, we'll do the change, and change of temperature is always final minus initial, so that's 100 degrees Celsius minus 0 degrees Celsius, so we have a total of 100 degrees Celsius change. So if I take 100 degrees Celsius change times my 4.184 joules per degree Celsius, we can do degrees Celsius and not have to use Kelvin, simply because 1 Kelvin change is 1 degree Celsius change. They're not the same, but the change is the same. And that means that there is what? There is 418.4 joules of energy to raise the temperature of 1 gram of water from 0 degrees freezing to 100 degrees boiling. It takes 418. The enthalpy of vaporization of water, okay, this is the H of vaporization of water, is actually 2,257 joules per gram. In this case, notice it's gram. I said 1 gram of water up here, but this is for degrees Celsius. It's actually gram degrees Celsius because that's the specific thing. This is just gram. It doesn't tell you about changing the temperature because we're not changing the temperature. This is 100 degree water, liquid, to 100 degree water, gas. Temperature remains the same. So I have 1 gram, and I take it times 2,257 joules per gram. Joules cancel out, just like degrees Celsius canceled out up here, and it takes 2,257 joules to to take water at the same temperature, 100 degrees, same temperature, but get it from the liquid phase to the gas phase. This is liquid, and this is gas. That's how much energy it took. It takes over 5 times as much energy to get water at the same temperature, 100 degrees, but get it from the liquid phase to the gas phase as it does to get it from 0 degrees Celsius to 100 degrees Celsius. That's why evaporative cooling works so well with water, because it takes so much energy. It also is why steam burns you so bad. Steam burns you so bad because when it goes onto your skin, it dumps all that energy on your skin and can really burn the heck out of you. So what you're going to do is you're going to take a thermometer that's in your kit, and you're going to take some filter paper, just some coffee filter paper, and you're going to take that filter paper and put it around the end of the thermometer, take a rubber band to hold that filter paper on there, and then put some water on there. And you're going to measure it over, I think it says 8 minutes. It's like every minute for 8 minutes. I can't remember right off the top of my head, but something like that. You're going to measure the temperature. And obviously with evaporative cooling, temperature is going to go down. Now you would expect, water removes a tremendous amount of energy, so it's going to really cool things down, and it would, but not quickly. Because it takes so much energy, and the only energy that's available is room temperature energy, which isn't a lot. Because it takes so much energy, water evaporates slowly. Now that's good for regulating your body temperature, because you don't want to be hot, and then all of a sudden, boom, you suddenly get frozen because it evaporates off so quickly and takes so much energy from you. Your skin freezes on the outside while you're boiling on the inside. Bad. So you want something that takes a lot of energy, but because of that, it's very slow. You're going to try this again with acetone, and you can get the acetone from buying some nail polish. Same thing, take a different piece of filter paper, put it on the end of the thermometer, put a rubber band on it, soak that into some acetone, and then set it down, tape it to the table the way they show you, and let it evaporate. You're going to find the evaporation is very, very fast. When you look at the structure of acetone, and you can look that up, you'll see why. Look at the intermolecular forces, decide acetone probably evaporates very fast, and that's going to cool things down much, much faster. Then they say to try it with isopropyl alcohol. If you can find it, great. If not, get some of the windshield washer and do it with methanol. And again, look at the structure of these different atoms, figure them out, draw the Lewis dot structures of them. You can look this stuff up online. You can use those resources, and you should be able to come up with why you saw what you saw. Then the other thing you're going to do is still involving intermolecular forces. You're going to take a penny that's dry and clean, set it on the table, take a dropper and put drops of water on it, and build up a bead, and you'll notice that water does something very weird. If the penny's sitting like right here, the water's going to bead up in this big bead like this. Why is that? Well, because water is sticky to itself. Remember hydrogen bonding? It's sticking to itself, so it's pulling in, sticking to itself. It doesn't stick to the air. So it doesn't stick to the air, therefore it pulls into this drop shape that it is. That's why water forms a drop. And then you're going to do the same thing. You see how many drops it takes to finally break the edge and spill over. And then you'll try the same thing with the methanol, try the same thing with the acetone, and see what you see, record your results, and explain your results based on the intermolecular forces. Very, very important stuff. Like I said, hydrogen bonding, that's what holds your DNA together. Kind of important. It also makes life on Earth possible. All right, that's pretty much everything I got. Like I said, I've kind of gone through the lab. Hopefully you get your kits by then. I'm going to do another survey of everybody on Monday to make sure everybody has their kits, because you need your kits to be able to do this lab. You don't need to be able to have your kits for the graphing part of the lab, and we covered that when we had our meeting. That was for last week's lab. I'm saying for last week's lab, you'll need that. Not this, and you do need it for this week's lab as well, because you're going to need the thermometer that they supplied. You're going to need some things that they supplied in there. A lot of them you have to go get at the store, so make sure you do go to the store and get those. Be careful, wear a mask if you want to. Try to go when there isn't a lot of people around, and keep your social distancing. That's all I have for this week. Again, give me some feedback. Let me know whether this video helped or didn't help, whether it was confusing or not. I know I went fast because I had a lot to cover, but most all of it should be a review. Only a few things should be new, and so it shouldn't be too difficult. Let me know if you have questions. If you don't understand what's going on, I'll put this video up on Friday. Therefore, you'll have a week, 2 weekends to be able to view the lab and work on the lab before you have to turn it in. And that should give you a chance to come and ask questions if need be. I can answer them by email. I'll answer them by email. If I can't answer them by email me. We'll set up a Zoom and we'll go through it and work it out. All right, stay safe. See you next week.